Hello students, welcome back to this lecture series. So in the last class we discussed some formula or the derivations of the Fourier complex integrals and the complex transformations. So in this lectures we are going to discuss some example on the complex Fourier integral formula and the complex Fourier transform. Okay, so first example, that is compute the functions f of x is equal to 1 for mod x is equal to or less than 1, and for the 0 the given the conditions mod x is greater than 1 as a Fourier integral. So we know the Fourier integral formulas, that is f of x is equal to 1 over pi integrations from minus 0 to infinity and again integrations from minus to plus infinity f of t cos lambda into t minus x into dy into dt. So this is a Fourier integral formula. So this f of t is given, that is equal to 1 or 0 for the given intervals. So if I put the f of t is equal to 1 for the first case, that is mod is equal to or less than 1, so we can write that is minus to plus 1, okay, for this limit. So here f of t is equal to 1, so 1 over pi integrations from 0 to infinity and again integrations from minus to plus infinity. So this minus to plus infinity we can write this mod is equal to or less than 1, it is implies minus 1. So here this minus to plus infinity we can write minus 1 to plus 1, okay, and for the f of t it is 1 into cos lambda into t minus x dy into dt. Okay, so this is now we have the expressions after substituting the functions and the limits. Okay, so now if I differentiate with respect to the t, because t is variable thing, so functions f of x is equal to 1 over pi integrations from 0 to infinity again okay, so 1 into cos, that is cos lambda, so cos lambda, or also we can write this cos lambda cos into lambda t minus lambda x, okay, in the, or also we can take out the commons for this lambda. So here if we take the integrations of this cos, so that is sin lambda t minus x divided by lambda, because we differentiate with respect to t, okay, and minus 1 to plus 1 into d lambda. Okay, so here now just substitute this limit. So if I put this upper limits, that is plus 1, and then the lower limit, so it is 1 over pi into lambda, okay, this lambda take out common, and 0 to infinity sin lambda t minus lambda x, so it is for the one we can write lambda minus x and then the lower limit, so minus sin to minus 1 or the minus lambda minus x into dt, okay, after substituting the limits. Now this minus sin minus x we can write minus sin x like this. Okay, so this minus become a plus and this expressions become f of x is equal to 1 over pi integrations from 0 to infinity sin lambda plus x, we can write like this, plus sin lambda minus x into d lambda. Okay, so this sin lambda plus x, or also here is a lambda, if we multiply. So this sin lambda plus lambda x plus sin lambda plus lambda minus lambda x, this we can write 2 sin or we know the formula, that is 2 sin lambda into cos, or the 2 sin x into cos y is equal to sin x plus y plus sin x minus y. Okay, by using this formula we can write this thing as a 1 over pi integrations from 0 to infinity 2 sin lambda into cos lambda x, okay, into d lambda. So or here is a into lambda. Okay, so this also we can write 2 over lambda pi integrations from 0 to infinity sin lambda into cos lambda x d lambda. Okay, so this is Fourier integrals for these functions f of x. So now here is one condition, that is x is equal to 0. If I put into this expressions, then this expression becomes f of x is equal to, sorry, f of this x is equal to 0. So this is f of function of 0. Okay. So it is equal to 2 over lambda pi integrations from 0 to infinity and sin lambda into d lambda. Okay, this cos lambda x is equal to 1, so 1 into sin lambda, so that is sin lambda. And if this f of 0 is equal to 0, then we can write pi over 2 is equal to integrations from 0 to infinity sin lambda by lambda into d lambda. Okay, so this is expressions. Okay, or we can directly use this formula for substituting. Okay, so this is about the this Fourier integral formula. We can use like this and apply for the functions, and we can evaluate the some expressions like this. Okay, so next example, that is about the Fourier transforms. Now f of x is equal to 1 minus x square, or the same mod x is less than or equal to 1 and is equal to 0 for mod x is greater than 1. So the compute the functions f of x as a Fourier transform. Okay, so we know the formula for the Fourier transforms, that is f of s. Okay, this s for the Fourier transforms. So f of f is a function of x is equal to 1 over under root 2 pi integrations from 0 to infinity or minus to plus infinity f of x into e raised to I x dx. Okay, so this is a Fourier transform formula. Okay, so now if I put the f of x is equal to 1 minus x square, so here the limit is minus 2 plus 1s. Okay, if we solve this, x is variable between minus to plus, and for these things this is equal to 0. So we just apply for this case, that is minus 1 to plus 1. Okay, so it is 1 over under root 2 pi integrations from minus to plus infinity. F of x is equal to 1 minus x square into e raised to I s x into dx. Okay, so here also we can write that this limit, that is minus 1 to plus 1. Okay, now 1 over under root 2 pi, if here is a two functions, this is one and this is another, so we can apply the by parts formula. So by using the by parts formula we can write integrations 1 minus x square and the integrations of this exponential term, that is e raised to I x divided by I into s, we differentiate with respect, integrate with respect to the x, so it is minus 1 to plus 1 minus integrations, that is minus 1 to plus 1s, and the derivative of this first function, that is 1 minus x square. So if we take the derivative, that is minus 2x, and the integrations of the second, so here e raised to ix to is. Okay, so this is the expressions because of the by parts formula, and we know the by parts formula, that is u into v dx is equal to u integrations of v dx minus integration u prime integrations v dx into dx. Okay, so this is the by part formula that I am using here. So 1 over under root 2 pi into 1 minus x square e raised to ix divided by is, okay, minus 1 to plus 1s minus, so this minus minus plus, so here also we can again apply the by parts formula, so we get the plus into x into e raised to I is x divided by I is bracket square, again differentiate, so this I into s square, so minus integrations, or here is a limit, that is minus 1 to plus 1, and again integrations minus 1 to plus 1s, and here minus 2x, so here is a x 1 derivative of the x, that is 1, and the 1 and the integration of this thing, so it is e raised to is x divided by is. Okay, okay, let me check this. So here is a square. Okay, so here if I again need this integrate with respect to x, so here is a thing minus e raised to is x divided by I into s bracket cube, and the limit, that is minus 1 to plus 1s. Okay, so this is total integrations of this two functions. Okay, so now if I apply the limit, that is minus 1 to plus 1s to this first expressions, then it is equal to 0, because 1 if I apply, then 1 minus 1 is equal to 0, and for the minus 1 it is 1, and 1 minus 1 is equal to 0. Okay, so for this it is equal to 0. So just we are going to think about these two terms, that is x into a raised to I into sx divided by is bracket square, and the e raised to is x divided by is bracket cube. Okay, so I think it is 2. Okay, this 2 is here. Okay, both the terms. Now for the second terms, if I apply the limits, then it is 1 over under root 2 pi. Okay, 2 for the x, that is 1, just take out the 2 is common, so e raised to is 1 minus 2 into e raised to minus, okay, then the minus for this 2 e raised to is, okay, here is also the same, so 2, here is a minus minus plus, because we apply this limit, lower limit for this second term, so it is plus sign, and the minus 2 e raised to is 1 minus e raised to minus is, okay, divided by is cube. Okay, so this is after substituting the limit. Now we can write these expressions. It is, if we take the 2 is a common from these two terms, then it is 2 by under root 2 by pi into e raised to is plus e raised to minus is divided by is bracket square and minus e raised to e raised to minus is divided by is cube. Okay, so this is expressions. So these expressions we can write e raised to is plus e raised to minus is, that is the cos is, and e raised to is minus e raised to minus is, that is the sin is. Okay, so f of x is equal to, f of s is equal to 1 over under, f of s is equal to under root 2 over pi into this, for these things we can write this is 1 over is square, and the cos is minus, for these things we can write we know the I square is equal to minus 1. Okay, so minus minus plus, so that is plus sign, and the 1 over I into s cube, I into s cube. Okay, so here we can write 2I sine s. Okay, and here is also 2. Okay, so 2 cos is, or also here this I square we can write the minus sign. Okay, so 2 over is square cos s plus 1 over I into s cube into 2I sine s. So this I we can cancel out, and finally the expressions 2 over pi into 2, or for the I square we can write the minus sign, so it is 1 over s cube 2 sine s, and the minus for this I square 2 over s square the cos s. Okay, so this is the expressions for the Fourier transformations of the functions 1 minus x square. Okay, so also we can modify by just take out this 2 is commons, and then this multiply with this under root 2, so we get the another expressions for the Fourier transform. Okay, so let's stop here, discuss in the next lecture.